I don't have any PhDs. He has 2, not even parapsychology. I'm ABD, which means all but dissertation. It also means almost but not quite a doctor. I'm as close as you can get without actually having it, but I've got a good reason for not actually finishing. So the company that I work for is Barico Technologies. It's a veteran-owned small business based in Reston, Virginia. It's basically a group of data scientists and software engineers and analysts, and we support customers primarily in the Department of Defense and intelligence communities, but that work is really expanding into the commercial space, and we do really cool stuff similar to what I'm going to be talking about tonight. So the problem that I'm trying to solve with the project that I'm talking about here is basically turning text into maps. So there's a growing demand for geospatial analytics. Otherwise, we wouldn't have a sellout crowd here. So everyone's interested in location-aware technology, geospatial data, but that data is often hard to get. Most of the data in the world that's generated is unstructured data, and a lot of that, or a vast majority of that, is in the form of text. Human beings don't generate machine-readable output. They generate language, either written, spoken, whatever. And we want to be able to make use of that information. We want to take all of these volumes of text documents and do something with them. And among the things that we want to do are geospatial things. So we want to take text and turn them into maps. The problem is there are tools that will do this that have been around for about a decade, and they're good, but they're really, really ridiculously expensive, like 7 digits licensing costs. So the barrier to entry for that is really high. Also, they typically have, we're in the age of big data, so we don't want to process hundreds of documents. We want to process hundreds of millions of documents, which means we need a lot of machines, which often means you have to buy licenses for all those machines for proprietary tools. And often there are per document costs. So you're paying $1 or whatever for every document that you're processing. If you've got a relatively small these days data set of 5 million documents, I don't have $5 million I can just blow on indexing that geospatially. So we want to have a open source geoparser. And what a geoparser is it allows us to turn text documents into maps or generate maps from text. And there's really 4 steps that you have to do in order to do that. And the first one is ingest unstructured text. And that can be news reports, that can be emails, social media, SMS, whatever sort of form you have of text that's been written by people. That's what we're going to take as input. So you have to handle all of those ingestion issues. The next step is to extract anything that looks like the name of a place. So we're doing entity extraction at this phase. Fortunately, there are some tools that already do this for us, some open source tools that are really good from the Stanford Natural Language Processing Group, and also Apache has some good tools. Obviously, the Apache stuff is Apache license. The Stanford stuff is GPL, Boo. The Stanford stuff is actually really, really good, though, and we use both. And what these tools do is they take that raw, unstructured, plain text, and they will automatically tag anything that looks like the name of a person, an organization, or we're interested in is locations. The way they work is they don't have just a big white list of known place names. They use machine learning models that have been trained on annotated documents that poor grad students have been chained to desks for semesters at a time, manually annotating. But those models are based on syntax, grammatical structure, the phrases. So it can be something completely made up. You can say, I went on vacation to Atlantis, and it'll say Atlantis looks like the name of a place. It doesn't know what it means. It just says, based on how it was used in this text, this string, this token looks like the name of a place. But we want to go deeper, right? So that's not enough to make a map from, because if it says Springfield and you say, hey, this talked about Springfield, the first question is, well, which Springfield are you talking about? So the next thing you need to do, and this is the hard part, and this is where the geoparser comes in, is you need to be able to disambiguate those place names, because just like with Springfield, you have multiple places that can have the same name, and you want to know which one the author was talking about. You can also have different names for the same place, like Ivory Coast and Cote d'Ivoire are talking about the same thing, and you need to know that they're the same thing. So most of the talk is about how we actually do this. The data set that we use to know what all the names of all the places in the world are is called geonames.org. It's a gazetteer It's kind of like the Wikipedia of gazetteers. It's Creative Commons license. And it basically has a record of every single place in the world that has a name. So every city, country, mountain, river, there's even buildings in there. So it has, and this is a heat map of all the different places in the world that are covered by geonames. So this is the gazetteer we use as our backing data set. And I've sort of hand waved over how we do that magic in step 3, but the end of the process is we get this structured geodata that we've now generated from the text. So we have all these places with lat longs and all these codes for, what kind of location is it, population, elevation, time zone, all this sort of stuff, and we can start generating maps from this. If you have a shapefile based gazetteer, you can produce the shapefile from that. So basically we get input comes as text, output comes as this structured data that you can then feed into whatever map visualization or geospatial analysis tool that you have at your disposal. So going back to that step 3, which is the hard part, one of the biggest challenges here is solving what we call the Springfield problem. So this is a map from USGS of all the different places in the US named Springfield. And there's like 3 or 4 dozen, and you'll see sometimes there's even multiple Springfields in the same state. There's no law that says 2 towns in the same state can't have the same name. I mean, the town I live in Virginia is one of 3 towns that have the exact same name in Virginia. So I mean, and mine is the biggest with 900 people. So there's a lot of ambiguity that we have to deal with. So what we use to handle this is natural language processing. So one of the cool things that happened while I was in grad school was when I first started grad school and working on NLP, no one had any idea what I was talking about when I said, yeah, I'm doing computational linguistics. And I would try to explain it to them, and they have no idea. So a couple of things happened while I was in grad school. Siri came out, and Watson came out. Watson, the IBM computer that won Jeopardy. These are systems that have NLP built into them, so I can say, hey, this is an example of NLP. NLP is a form of, or a subfield of artificial intelligence, and we're using computers to analyze human language. It's not perfect, right? Anyone who's used Siri before has encountered frustrations. And it's not just Siri. Anyone who's used like Google Translate or machine translation tools know that you often don't get what you expect. And it's not just dumb Americans who don't know any other language but English. This was at the Beijing Olympics, so somebody had to make bilingual signs, and I don't know what this means in Mandarin, but it doesn't mean translate server error. And they printed this like 10-foot tall sign from that. And even when NLP is really good, it still makes mistakes. I mean, Watson wiped the floor with these guys. I don't know if anybody watched it, but the actual final question. Watson was so far ahead that there was no way for it to lose. But the final question was something like, this American city, blah, blah, blah. And Watson's, the question / answer that it provided was, what is Toronto? Right? And every third grader who's had a geography class is like, no, you idiot. Toronto is not an American city. So it'll get things wrong because it's doing these tricky statistical inferences behind the scenes. Watson doesn't actually know what's going on. It's using all of these tricks. And some of those tricks are what we're doing, and I keep saying I'll get to it, and I will. So we built that, right? So we built a tool to do those 4 steps, to be a geoparser, to go from unstructured text documents to structured geodata that you can then use to generate maps and do other geospatial analyses. It's called CLAVIN, which stands for Cartographic Location and Vicinity Indexer. It's also named in honor of a certain 1980s sitcom character. And I liked it because it allowed us to have a postmark with a mustache as the logo. So a little bit about the system architecture. Again, the input to the system comes in as an unstructured text document. We work 1 document at a time, whether it's 10 documents, 10 million documents, we treat each one separately. The first thing that happens is we run it through one of these third-party named entity recognizers, like the Stanford tool or the Apache tool. And from that, we get a list of location names. So it says Springfield, Arlington, Portland, right? It doesn't know what they mean. It doesn't have a semantic understanding. It doesn't know that these are cities with lat longs, and it doesn't know the difference between Springfield, Missouri, and Springfield. Exactly, yeah. But it just says these are names of places, and the magic happens in the middle. So what we do is we take that geonames.org gazetteer, which has records for 8-point-something million locations with about 16 million unique names, because the same place can have multiple names. We take all those records, we load them into a Lucene index. So Apache Lucene is a full-text indexing system. And so we, for anyone who's a Lucene hacker, we essentially treat each name as its own document, which is sort of a weird way of using Lucene. But it lets us take advantage of a lot of the speed that Lucene provides, some of the built-in things to deal with fuzzy search, so we can handle misspellings, whether typographic or phonetic. Working with data from Afghanistan, I can't tell you how many different ways I've seen Mazar-e Sharif spelled incorrectly. One of the main things that we have to do is deal with the Springfield problem, right? So there's a whole bunch of heuristics that we use to determine which is the right Springfield. So we have, if we go back to our slide here, we've got 36 different options to figure out which is the right Springfield. So if we know nothing else at all, we'll assume that all else being equal, places with higher populations or larger populations are more likely to be talked about. So if we see Paris being mentioned, our first assumption is they're more likely talking about Paris, France than they are talking about Paris, Texas. 2-point-something million people versus like 2,000 people. But sometimes they are talking about Paris, Texas, and we want to be able to realize when they're talking about Paris, Texas. Another thing we look at is what are the other places that are being mentioned in the same document, in the same context. So with Springfield, if we see Springfield, like, well, is this Illinois, Massachusetts, Missouri, whatever. But if we see Springfield and Boston together, that's a big clue that we're talking about Massachusetts. Or if we see Springfield and Chicago together, it's a big clue that we're talking about Illinois. And we can also look at the distance between things. The distance between locations. More likely you're talking about locations, especially when you're in a list, places that are near each other or of similar types. If you're talking about cities, if you're talking about some cities, you're probably talking about other cities. If you're talking about countries, you're probably talking about other countries. So there's a whole bunch of things that go into it. It's really good to just jump in and give a demo. So let me do that. So this is the CLAVIN website. Has a link to all the source code and everything. And this is the GitHub page where it's real open source. Anyone can get it. So let me jump into the demo. So this is not CLAVIN. So CLAVIN is just a software library and some data. This is a really, really simple web app just for people to be able to try it out and see how it works. No one would actually use this really kitschy interface for their actual work. So it might be a little small to see, but I can say something like this. I was born in Springfield and grew up in Boston. And we click on Resolve, and we get a map of Massachusetts. Behind that map, there's some more structured data with lat longs, and there's a whole bunch more like I was showing before. There's just not enough room to show it on the screen. So if we go back and we change that from Boston to Chicago, we get a map of Illinois. We can say something like this. Grover Cleveland was the 22nd president of the United States. He was also the 24th, 2 non-consecutive terms. That's a Cliff Clavin trivia fact. He never went to Cuba. I don't know if that's true. Makes the map look better. So Clavin is smart enough to know that Grover Cleveland is not a city in Ohio, because the entity extractor has said Grover Cleveland is a person and we don't care about people, or we don't care about locations. So we only get pins on the center of the United States and Cuba. Another thing I can do, this is sort of sad. This is a CNN article about a natural disaster in the Philippines from last year. And I've been using this because there's something cool that happens when we run this. And it's unfortunate that the Philippines are suffering from another natural disaster right now. So this is about a page or two long, talks about a bunch of places. You'll notice that there is sort of a generic map here of the Philippines, but there's nothing special about this map that's relevant to the article other than the article's talking about the Philippines. But if we copy and paste that text into CLAVIN, we quickly get a map of all the different places in that document that are talking about the Philippines. One thing I like to point out is right here, Boston. And you say, Boston, but I don't see Massachusetts here. Oh, Charlie, you got something wrong. And I say, you really think I would give a demo with data that didn't actually work? So it turns out though, even though 99% of the time when you're talking about Boston, you're talking about Massachusetts or maybe the little city in England that it was named after. There was actually a village in the Philippines named Boston. And see right here, so CLAVIN was able to figure out that even though 99% of the time you're talking about Massachusetts, there was enough context here for CLAVIN to see they got the needle to flip over to Boston in the Philippines. So let me jump back into the slides here to keep things rolling. Okay, so you got that, right? So we got these places from text. Well, what are you going to do with this data, right? So you've taken your unstructured text, you've turned that into structured geodata. What can you do with it? Well, obviously you can do map visualizations like we see in the simple demo. Given a single document, you can put pins on a map. Given a huge collection of documents, maybe you can do some kind of heat map where you see which countries are being talked about. You can zoom in into provinces and cities. But that's just one thing you can do. Another thing you can do is what we call hierarchical geospatial search. And this is a form of semantic search, where you're not just searching for keywords, you're searching based on concepts. So let's say you wanted to search for something and you wanted only to get documents that were relevant to Virginia. Well, if you use Virginia as a keyword, that document the only documents you'll get back are those that explicitly mention Virginia. But not all documents that are talking about Virginia even say Virginia. Sometimes they talk about Reston, sometimes they talk about Arlington, Alexandria, there's a Springfield, Virginia. And we want to get those back because those are conceptually, those are administrative subdivisions of Virginia, so they're relevant to Virginia. So by processing those documents with CLAVIN and then indexing it based on that geospatial semantics, we can retrieve those documents when we search for Virginia. So you'll get these documents back that talk about Reston, they talk about Arlington, even if they don't explicitly mention Virginia, because we have an understanding of what these names mean, we can return those in our search results. Another thing you can do is another form of search where you throw away your search box. You're no longer typing in a keyword or anything. You're going to search from the map. So you can a user can draw a bounding box or arbitrary polygon or a circle and a radius and say, give me all the documents that talk about locations that fall within this box. And so all of those documents have been processed. They talk about places that have lat longs. And we can do like a range query to find out that those documents are talking about places that fall within this box and then return it to the user. Users really kind of like that stuff. And there's a whole bunch of other stuff you can do. Once you've got this data, you can feed it into whatever existing geospatial applications you've got. This is a tool that we've worked on, which is looking at different data sets and is showing the geospatial context of what's going on. I think this is a database of documents talking about terrorist incidents and showing which countries are being mentioned most often. So this is my only slide that has real bullets. Just some quick facts about CLAVIN. Again, it is an acronym. I don't want CBS suing me. Cartographic Location and Vicinity Indexer. So in terms of accuracy, the way you measure a tool like this is with a metric called F-measure, which, to get nerdy for a second, is the harmonic mean of precision and recall in terms of type 1 and type 2 errors. So we care about true positives, false positives, that sort of thing. Because we rely on the output from the extractor as our input, we can never do better than the extractor does. And most extractors, depending on the data, will get anywhere between 85 to 95% accuracy. So that's really our ceiling. And then if you look at if you run this task on humans and see what they do, humans are going to get about 90% inter-annotator agreement. So two humans will only agree about 90% of the time on what they're getting. So 76% F-measure, you can think of it sort of as 76% accuracy, is about as good as you can get with any of these tools right now. And and that's for exact resolution. So that's down to the exact lat long. So we were comparing against human output, and CLAVIN had to get the exact output that a human gave in order for it to be counted as true. So if the document talked about New York and CLAVIN says, I think that means New York State, and the human said, no, you idiot, that means New York City, we considered that to be as wrong as saying Azerbaijan. So it had to be the exact thing. So if your sensitivity is less, if you have a higher tolerance for horseshoes and hand grenades, obviously your score would go higher. It works really fast on a single machine, single-threaded, single CPU, no parallelization whatsoever. Running on this machine, it'll do 100 locations per second. It scales horizontally really well. If any of you have used Hadoop, it's essentially a map-only, map-reduced job. So it scales horizontally well. It'll do 1 million documents in an hour on a 9-node cluster, which is pretty small. There's a lot of cool things under the hood that we talked about. Really simple to use Java-based API. My colleague Travis is working on some REST interfaces and different ways to connect to it. Really easy, very commercial friendly, open source Apache license. You can get it on GitHub, you can get it on Maven. Those are our latest stats on GitHub. And the easiest way to get more info, You can tweet me. You can go to clavin.io for the website. And I'm out of time, so thank you for listening to me.